Okay, my friends, so we are going to be covering all things rational today. I think what I'm going to do is split it into um, rational function expressions as like a vibe, and then operations on them, and then we'll talk complex fractions. I think I'll do 2 or 3 separate videos. I'm not entirely sure yet, okay? Okay. Now I'm holding your hand gently when I say this, okay? Please, 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 please. If you're bad at fractions, please go back and get very comfortable adding, subtracting, multiplying, and dividing fractions. Because if you cannot handle fractions, this unit is going to be a nightmare, okay? Okay? Okay. Second, if you're bad at factoring, please, for the love of God, get really good at it. You should not be watching this video until you can do fractions and factoring in your sleep, okay? Please. Thank you. Okay, so let's give some definitions and go right into it, all right? I'm trying to keep this as short as possible, okay? So first, let's talk about what a rational expression or function is. Two separate ideas, okay? So, rational expression. Okay, first off, hear me out. We know what an expression is, so we'll define what a rational expression is, okay? Let p of x be a polynomial. Similarly, let q of x be a non-zero polynomial. Okay? Then p of x over q of x is a rational expression. Okay? Now let's define a rational function. Okay. With the same setup, okay, with the exact same setup, p of x is a polynomial, q of x is a non-zero polynomial, then f of x equals p of x over q of x is a rational function. Okay? The f of x is a rational function, okay? Easy. But when we talk functions, we need to talk range and domain and all that good stuff, okay? Okay. Now the next question is, what is the domain of a rational function? Okay, the domain of a rational function can be described as follows, okay? Actually, let's back it up. Let's just look at a function, okay? Let's look at f of x equals 1 over x. What values can x equal such that f of x spits out a legit answer? Can you have negative numbers? Yes, you can. Can you have positive numbers? Yes, you can. Can you have fractions? Sure, why not? Can you have decimals? Who cares? Can you have x equals 0? No. You cannot have x equals 0 because 1 over 0 is undefined. Does not exist, undefined, okay? Which means for rational functions in general, right, you do not want the denominator to equal 0, okay? And so if we bring it back to our general rational function, right, f of x is equal to p of x over q of x, the domain is all real numbers except wherever q of x equals 0. Okay? Grade scope question. Why? Okay? That's it. That's the intro to rational functions. Your practice problems, I want you to do what's listed here, okay? And in particular, what I want you to make note of is simplifying ratios of -1. I didn't show you any examples, but that's because I expect you guys to know how to factor out -1, okay? So give these problems a try, see what happens. I think number 55 has a typo, which I think is kind of funny. Yeah, all right. Yeah. If you do not know how to graph a polynomial equation, lock in, okay? Here are some things. 1, let p of x be a polynomial, okay? 2, let k1 of x times k2 of x times kn of x be the complete factoring of p of x, okay? If we have this set up, then you know let k1 of x to the power of I sub 1, j sub 1, hear me out, times k2 of x be to the power of j2 sub 2, j sub 2 times kn of x to the j sub n, right? Be the complete factoring of p of x. So for example, let's say you have p of x completely factored out equals x minus 7 to the third times x squared plus 9 times x to the fourth, right? That's all this means. It's completely factored. You have some fully factored form on the inside, so like you can't factor this anymore in the real space, right? You can't factor this in with these are linear factors, so on and so forth, right? Then 3, you have the zeros of p of x is wherever is whatever x values that make p of x equal to 0, right? And so if we go back to our factored form, you'll want things like x equals 7, can't do much here, right? Because it's x squared equals -9, you can't do that, and x equals 0, right? You take these numbers, you plug it back in here, you get 0, yep? Goes back to our like solving polynomial equations, right? The zeros of p of x is whatever x values that make p of x equal 0. The multiplicity of each 0 is the j sub I, or is j sub I. So for example, x equals 7 has a multiplicity of 2, x equals 0 has a multiplicity of 4, and both are even. Let me throw in one more. Let me throw in x plus 1, so you have an odd multiplicity, right? And x equals 1 has multiplicity of 1, which is odd, right? Okay? And finally, right, when p of x is in standard form, so a sub, what number was I using? A sub I of x to sub x to the I, a sub I times x to the I plus a sub I minus 1, x to the I minus 1, a sub 0, x to the 0, which is a constant term, right? When it's in this form, make note of degree of poly, which is your I value, and positive or negative a sub I value, okay? We're gonna take all of this, smush it together, and you can get a graph, okay? And by that I mean, by that I mean, first, your degree, even or odd, tells you symmetric or asymmetric, okay? Coefficient, positive or negative, tells you direction, okay? for grade scope purposes, I want you to tell me the following combinations, okay? So degree goes this way, and coefficient goes this way, okay? If your degree is even, your coefficient is positive, what does your graph do? Does it do this? Or like, does it do this? What does it do? Okay. Your degree is odd, and the coefficient is positive, what does it do? If your coefficient is negative, how does it affect the graph? And for even and odd as well, okay? So this is your grade scope. Use Desmos. Okay. All right. Now, the second thing that you can use is your zeros. Even multiplicity means you bounce off the axis. Odd multiplicity means you pass through. No solution, so like x squared plus 9 means you wiggle around until the next zero, okay? So what I mean by that is you can use strictly these details and graph everything you know about your function, okay? So for example, if we go back to our example, I can tell you off rip, loosely, what my graph is doing. Okay, so my leading coefficient is positive 1. If I multiply it out, I'm going to get positive 1. If you want to know why, work it out and find out, okay? Leading is positive 1. Okay, so that means my function is positive. Good. My degree is 3, 4, 5, 9, and 10. 3, 4, 5, 9, and 10. Yep. So the degree is 10, which is even. Okay, immediately I know that the end behavior of my graph does something like this. Okay, now let's start talking zeros, okay? I like to work zeros left to right. So from the lowest zero to the highest. So we're going to start here, followed by here, can't do anything here, followed by here, okay? X equals negative 1 has an odd multiplicity. So at negative 1, let's put this here. I know that my graph will pass through, so it'll go something like that, okay? And it's going to keep going down. And then at x equals 0, it has an even multiplicity. So I know that at x equals 0, so right about here, it's going to hit the 0, right? But it's not going to pass through, it's going to go back down, okay? And finally, for x equals 7, it's an odd multiplicity, so I know it's going to pass right through. So let's say x equals 7 is right about here, oops, right about here, right? You know it's going to pass through, and because the end behavior goes up, you can just connect it, and ta-da. At some point, for x squared plus 9, it's going to do a little whoop situation. You don't have to worry about that, okay? Punch this into Desmos and see what it gives you, see if I did it right. It ain't bad. I never said I had to get the dips perfectly right. I just said I have the general vibes of the function, you know? This could be you. This could be you. Anyway, let's talk about graphing our polynomial, our rational function now. It actually works pretty much the same way. Let's say f of x is equal to p of x over q of x, right? Well, first, you know, asymptotes are where q of x equals 0. So do that out, and you have your asymptotes. Cool. Okay. Second, end behavior is p of x. It's determined by p of x, okay? Your end behavior, loosely speaking, is determined by the degree of p of x minus the degree of q of x, okay? So if it's odd, it'll behave, you know, the way odd polynomials do, loosely speaking. If it's even, it'll loosely behave the way even polynomials do, okay? And it's end behavior, so of course stuff in between might do a little funny. And of course it might not like shoot off into space like that, right? Sometimes you might get like, right? Where this is technically going up, it's just very small. And this is technically going down, but just really small, right? Oh, and of course, if you have the degree of p of x minus q of x, and this is less than or equal, the end behavior is determined by both the degree of the numerator and denominator. So what you would do is you would say like, if you have p of x over q of x, right? If the degree of p of x is greater than the degree of q of x, right? Then you divide the leading coefficient of p by the leading of q, right? As to say, for example, if you have like 3x squared plus 7x plus 1, and you divide it, and you have it divided by like 7x squared plus smaller things, right? Fundamentally, these don't matter. You're learning calculus, limits of infinity, basically, right? And that all gives you, oh, these are the same. That gives you 3/7. So your horizontal asymptote is y equals 3 over 7. Okay. And then similarly, if the degree of p of x is equal to the degree of q of x, then you have a slant asymptote, which will have to do polynomial long division, which for our purposes, I'm not going to make you do, okay? Not going to make you do. That's a pretty tough problem. And then if the degree of p is less than the degree of q, then your asymptote is y equals 0, okay? Now whether it flip-flops or not is going to be up to the asymptotes, okay? So big picture, you have, this is your vertical, sorry. Vertical asymptote is wherever q of x equals 0. Horizontal or slant asymptotes are dependent on the degrees. Because big picture, it's how things divide out, that's all. And then, you know, you can talk multiplicities, right? Once you have all this down, you can start saying things like, oh yeah, well, p of x equals 0 are the zeros. P of x equals 0 and q of x is not 0. Because if q of x and p of x are both 0, that's called removable discontinuity. We don't have to worry about that yet. But it's not part of the domain, so you can't graph it. Then it becomes the zeros of the function f of x. Okay, and then the whole multiplicity business applies. All right. This isn't the most pertinent thing in the world. I want you guys to just kind of loosely be able to visualize where asymptotes should be and whether a function is like shooting off into space, which is where you have your slant asymptotes, or if they're doing some other funny behavior. Okay. Okay. Now, finally, the most important part is simplifying rational expressions. Okay. So 1, factor p of x and q of x completely. 2, determine if there are any shared factors on top and bottom. Cancel out, make note. Okay? Because just because it's simplified doesn't mean that it makes the expression true. Okay, let's do an example. Suppose I give you x squared minus 4 all over x squared plus 5x plus 6, right? If you do this, you end up with x plus 2, x minus 2, right? And if you simplify this, you get x plus 3, x plus 2, right? These are the same. There's no denying it, okay? Now, if you do step 2 and you determine if there's anything that's similar on the top and bottom, you'll find, oh, these are, okay? Make note. Because on the bottom, this is still a restriction even if you cancel it out, okay? You have to know x does not equal negative 2, all right? So then you simplify and you end up with x minus 2 over x plus 3. But remember, that restriction still holds, right? Just because you cancel it out doesn't mean that the problem goes away. It's still discontinuous there, right? So you have to note everywhere except x equals negative 2, okay? So this is equal to this everywhere except x equals negative 2. I'm only going to write this once, okay, because it's implied from the original equation, or the original expression, okay? The reason we want to go to simplify is because it makes plugging stuff in and moving things around a lot easier, okay? This is also what they call a removable discontinuity, okay? So, yeah, pretty easy.